The 16th question. Now let's see, there's a small bar magnet and it's been placed with its axis at an angle 30 degree with an external field. So let me quickly make a figure here. It's something like this. This is the magnetic field, and then let me show the moment. So it's something like this. So here we are done. This is the moment, and this makes an angle 30 degree with the magnetic field. The magnetic field is 0.06 Tesla. This is how it goes. Now at this particular situation, it experiences a torque of 0.018. So I think from this data we can calculate the value of magnetic moment, and after that we need to see the minimum work required to rotate from its stable, that's at theta equals to 0, to unstable position. Let's see, on the basis of the fact here 0.06, that is the magnetic field, multiplied by m multiplied by sine of 30, so that's 1/2. This is the value of torque, right? Bm sine 30, and this particular torque is equal to 0.018. So we got that value. Now from this, if you calculate, you get the value of m as 0.6. The unit of course goes as ampere meter square. That's the magnetic moment. Now the second part, the work required to rotate it from stable equilibrium to unstable equilibrium position. And the minimum work, that means the entire work would be focused only for potential energy. The change in kinetic energy would be 0. So what would be that work? The final potential energy will be mb at theta equals to 180 degree. And the initial is minus of mb. So this comes out to be twice of m multiplied by b. Here you have magnetic moment, here you have magnetic field, and you calculate that, the work done will come out to be 7.2 into 10 raised to the power minus 2 joule. Option number 3, that's the correct one. The next one, and here is from current electricity. There is a battery of 3 volt connected to a resistor dissipating 0.5 watt. So on the basis of this thing, what is the diagram that we can make? It's something like this. The EMF with the internal resistance, and here is the load resistance. This is 3 volt and it's connected to a resistor which dissipates 0.5 watt of power. So that's there. And even it said the terminal voltage of the battery is 2.5 volt. That has been given. So let me just indicate the terminal potential difference, which starts from here to here. And that potential difference, it has been given plus minus of 2.5 volt, right? That's there. Now this 2.5 volt is the entire potential difference. So what we can see, on the basis of this data, we can easily calculate the value of resistance, because this 2.5 volt is also the potential difference across resistor. So this is going to be 0.5 watt will be equals to V square upon resistance. And this value of resistance can be seen, that is equal to 12.5 ohm. So the first job has been done. And eventually we need to calculate the power dissipated within the internal resistance. That's what we need to do. So here, once the value of resistance is known, the potential difference is known, I can easily compute the value of current. And how much will that current be? That current is the potential difference 2.5 divided by the resistance, that's recently calculated, 12.5. And this current will come out to be 0.2 ampere. That much is the current. So any way around now you do, either you calculate the internal resistance and go with I square R, that will be the power dissipated in that, or you can also go in this way, how much is the power generated by the battery? So that is going to be 0.6 watt, right? Because this 3.2, so 0.6 watt will be equals to the dissipated across the load resistor is 0.5, and remaining would be the power dissipated across the internal resistance. And this value will be 0.1 watt. And where is that? Yes, we have option number 1. Question number 18. Question number 18 is from Semiconductor. This is the segment which is quite favorite for JEE Main. But here, this time, a little bit of modification has been made. There is an arrangement where the input voltage is applied, which is of this nature, the sinusoidal with the peak 10 volt. And there is a Zener diode mechanism. Now you could see the Zener diode mechanism is something like this. Here, and this goes in this way. This is the Zener diode mechanism, right? Let me just expand the figure. And we need to see how would the variation of potential difference across this, the entire, go when the supply voltage is this much. Let's see. Initially, let's talk about the positive cycle. Now just see, the voltage increases from 0 going to the journey of 10 volt. During that instant, initially, one diode in the positive, that's conducting, the upper diode. In the positive cycle, diode P would be conducting, diode Q would be reverse biased. But so far, the diode Q has not reached its breakdown yet. So now just understand the whole story, because out of these two diodes, one is reverse bias. So it clearly says, of course, the value of current through this resistor would be 0. Still, the breakdown has not been reached yet. The graph underlying for that is this, isn't it? Let me just show the graph of current versus potential difference, and that will give you the nice visualization. Now, let's just think about the reverse bias condition. A very, very, very little amount of current would flow, almost equal to 0. So what would happen? As the current is 0, the drop across the resistor would be 0. So it indicates whatever is the potential difference, the same potential difference will appear between these two terminals. This is till the instant the diode has not reached the breakdown. So whatever is the potential difference, that will be copied. Once the diode reaches the breakdown, now you should understand the potential difference, that would be fixed. That's the characteristic of Zener diode, right? Because once the breakdown reaches, the potential difference is constant. So the option would be, it's clearly visible, it's option number 3. Because see, initially the potential difference increases, and once the breakdown reaches, the potential difference will be clamped, that's constant. And after that, again you would see the potential difference would be clamped on the negative part. So out of all these 4 figures, option number 3 is the best which resembles. Let's go to the next one.